Hi everyone, and welcome to part 2 of large language models as general pattern machines. So last week, what we did was we talked about this paper. We talked mainly on the first two, like the sequence transformation, which is basically how you use large language models to try to figure out unknown rules, like for the abstract reasoning corpus, how to make like chunks of cells connected together and then find the maximum color or like the most common color. That's what you see in this puzzle here. Object rearrangement, try to predict where the gripper arm is, or try to predict the next state of a particular action, such as moving the red color bowl to a green color bowl. Right. So this thing here, large language models can do it pretty well for patterns that are easy. Okay, I mean, I tried the ARC corpus myself, ARC challenge myself, and it can work quite well out of the shelf for common patterns, like for example, translation of an object. Okay, but if you want to do stuff like if the object has more than 6 cells, change color, you know, those kind of stuff, you kind of need to prompt it more with like the specific rules as the context. Okay, if not, asking it to generate arbitrary rules may be difficult. Okay, but this is an interesting use case of like how you can just use the large language model to do simple pattern matching. Right, the second case here in the center is sequence completion, whereby we try to do extrapolation of maybe a time series, like a graph. We try to extrapolate it. Again, a large language model may not be the best use case for this because, as I mentioned last week, the tokenization for numbers may not be very good. Okay, it is better for words. Okay, numbers it's not exactly able to perform tokenization of the number line that well. So, like for example, if you have a number line like that, you have a 0 token here, maybe you have a 1 token here, you have a 2 token here. By right, your 2 is supposed to be like double the length of a 1, all right? But if you were to train this using backprop, you may not get this kind of relation. So like the number magnitude is not innate in embeddings. Yeah, so if you want to do sequence completion for like this kind of numbers, it's not ideal. It's best if you could map like maybe the numbers to certain things like A, B, C, A. Then you can like do some form of pattern matching with the symbols. That will be better for a large language model. Right, and lastly, we talked about pattern sequence improvement, and this is the part that we'll be focusing on today because last week we didn't have time to finish this, but sequence improvement is basically using the large language model to improve on given sequences to increase the reward obtained. So essentially, it is trying to do reinforcement learning by improving patterns, by taking the previous patterns as the context and trying to find out another sequence that will give you the maximum reward. All right, so this, I think it's an interesting idea, but let's see how we can improve it. So this is what I was talking about. Just a recap. So like you can either like transform the sequence like A to B, B to C, C to A, or you could do some like extension of the sequence like that. This is a sequence completion. Or given arbitrary reward sequences like this, like reward 0, reward 1, we want to get reward 1. Okay, and in this case, reward 1 will end with D. So we see whether the large language model can figure this out. Right, so let's move to the slides that I wanted to talk about today. So this reward thing is mainly based on this thing called the decision transformer. So given a rewards to go, all right, rewards to go is like the total reward we will get from the environment. Okay, so given this rewards to go, okay, we try to predict the next action. All right, given the rewards to go and the current state, we predict the next action. So this next action that is predicted will be used here in the transformer again. Okay, and we will get the rewards to go for the next state, which is basically after you take the current action, like let's say you get a reward of 1 for this time step. Okay, and the total reward we want to get maybe for this Pong game is 22. All right, and you got reward for 1 for the time step. You minus off that reward you get, and then you get the next reward, which is 21. Okay, and then you give the next state and so on. Okay, and then you can predict the next action. So this is basically using transformers, okay, with the previous reward states and actions as the context. Okay, try to predict the next action. Okay, so this is the decision transformers. And they tried to implement this on card pull. So it's quite an interesting attempt. And yeah, you can see that like this is the total reward we get for card pull. For card pull, the reward is you get 1 reward for every time step of survival. So 60 means you survive for 60 time steps. And then they discretize the states. into bins for the pole angle and the velocity. And so 2 or 1 is for the action either left or right. So 2 is probably right and left, 1 is left. And so you try to balance the card pole. So given this as context, okay, you try to give like maybe the next observation, maybe you want to give a random reward like that, 101, you give your starting state, and then you try to predict the next action, predict action. Yeah, so this is what they did. Last week, I said about how we can tokenize these numbers by saying that like you can manually take this text out, and then you can manually encode this into a token, right? So that you don't lose the meaning of this. So you can encode this manually into token. Okay, I went to look at their code again, and I realized that in their code, they did not do this. Okay, so they just tokenized this whole thing as text. So they basically feed in this sequence as text and then let the tick token tokenizer do something about it. So this means that for these numbers here, like 4550, there's a chance that it might be split, like the 4 and 5 might be split away from each other and not tokenized together as 45. Okay, that's probably why one of the reasons why this method that they did may be inferior. Okay, you should actually encode this manually into a token if possible. Okay, so this is the result that was shown last week. Okay, this is basically saying that it takes very long for the sequence improvement to learn to reach a return of 200, which is like you survive for 200 time steps, which is the maximum for couple V0. So you can see that it even for the largest models, C1, it takes about 90 over episodes. Okay, because the first 100 are random for exploration. It still takes about 90 episodes to learn. And PPO can learn like 1 episode. Within 10 episodes, confirm you will learn. So it's very inferior to like current reinforcement learning architectures. Okay, so this is the thing that I wanted to talk about today, is that is learning reward to condition your action on reward, is it really necessary? Like a lot of things right now, we talk about RLHF, okay, reinforcement learning from human feedback. Stuff like this still gives a very sparse reward signal. So in the RL environments they actually have kind of auxiliary rewards. Like for example, in the grid maze, which is you have an agent here, and you want to, kind of like my experiment actually, you have an agent here and you want to get to a goal state here, right? Instead of just giving it a reward of 1 or 0 for reaching the goal, we also have a Manhattan distance reward, like basically based on the distance that we have from the endpoint to goal, the closer it is, the more reward. So you can see it here. So this actually helps the agent to learn, okay, I need to get closer to the goal. You can see this is the reward that they use, right? Which kind of hints that, maybe just using a reward signal to learn something may not be the best case, right? Last week, I gave an example, like if, for example, you want to learn a new language, like let's say we want to learn Singlish. So if I say like la, le, lo, as long as you use these words, it's considered use Singlish, right? But I don't tell you what Singlish is. I only give you a score of 1 to 5, of 0 to 5, based on how close you are to Singlish. So if I were to train you in this kind of manner where, like just give you a number score for learning how to do it, it kind of feels difficult, right? So you all agree, right? If we just use the reward itself without telling you how to achieve it, okay, it can be quite difficult to learn, right? Like, the card pull that we saw earlier, we did not tell the AI at all how to play the card pull game. Just like for humans, you know that, okay, if we play the card pull for humans, I'm going to tell the human, you are to balance the cards. You can move the card left or right, and you are to balance this pull. So this information is already given to the human, right? But we don't give this information to the AI. The AI is just like, oh, what's this environment? I'm going to just try this out, try things out. And then, oh, reward of 1 means I'm doing something good. Reward of 0, I'm doing something bad. So this is great if you cannot describe your environment in words. But with today's technology, like large language models, this kind of thing feels a little old. Like we are essentially asking the AI to learn without telling it what it needs to do. So we're just telling, okay, you just maximize your reward. Okay, sure. I mean, that works for simple problems, but for more complex problems, it's going to take forever for the reward to even be translated to your actions. Okay, especially for sparse rewards domains where like only maybe after 100 sequences of maybe moving up, they reach the door, then you get the reward. Those stuff like this will take forever to learn with reinforcement learning. Okay, even AlphaZero. Okay, AlphaZero, the reward for the there's a value network. The reward for the value network is based on how different the outcome is from how different the let's say for each goal bot here, you have an intermediate goal bot state here. We see what's the value of the state. So we actually predict two things for each moment. We predict the value of that state T, the goal bot here. We predict the value of that state, and we also predict the distribution of that state, which is like the distribution of moves given that state. And this value here, okay, eventually once we reach the end of the game, let's call it ST. Okay, we will either get a lose, a draw, or a win. Okay, and what AlphaZero does is that it tries to match every single time step prediction of this. You try to match this with this, okay, using mean square error. Right? So we try to force the prediction of the outcome for each state, okay, with the end outcome. Okay, and that's actually not that great because like sometimes you made a good move, but the outcome is bad, okay, because maybe you made a bad move later. So how can you actually like learn whether or not your move is correct? So this is not a very good loss, okay. Unfortunately, that's reinforcement learning. You can only learn from the end outcome, right? But what if you can learn from like somewhere in the middle, like an intermediate outcome, that you will learn much faster, right? And that's actually what they did right for AlphaZero. They actually have this distribution here, okay, which is basically the what moves to make in order to win. So they use Monte Carlo tree search here, Monte Carlo tree search to find out after the tree search what are the more promising moves. Okay, and after you find out what's the more promising moves with Monte Carlo tree search, okay, sorry, the Monte Carlo tree search is here. You do a Monte Carlo tree search based on the original state. You search for the more promising moves after that. Like you form the tree here. You search for the more promising moves. And then after that, you match with the predicted move distribution by your neural network. So this is what I call the Monte Carlo tree search based policy improvement. You improve the policy of predicted moves, like the probabilities of winning moves, by doing a Monte Carlo tree search. And you use that Monte Carlo tree search as a way to improve the estimate that you have. So this is something that is quite cool. And I think this is something that caused it to do well, right? The Monte Carlo tree search. Not so much this outcome here, but the Monte Carlo tree search here. So this just hints to me that like just having the reward alone is very long to train and it may not be the best. And you can see in a lot of modern reinforcement learning methods, especially this new branch called the offline RL methods, they use behavioral cloning, whereby they just learn from expert trajectories. Yeah. So like a lot of very, very famous models like Gato, the one by DeepMind can do a lot of games. They actually learn from expert trajectories. And it essentially becomes a mimicking game. So you mimic expert trajectories. Great is a great starting point. But how do you get the expert trajectories in the first place? You still need to learn from somewhere. So all these problems have hinted to me that reward-based learning is not exactly ideal. Maybe we need to do something called goal-directed learning, which is we learn from goals. Okay, so how far are you from achieving your goal? Like for example, this maze over here, how far are you from achieving this goal? If you can measure in some metric space, you can essentially learn from any single point of your experience. So I think this is a way better way of learning. Yeah, but before I move on to exactly like how I intend to do this, do you have anything you want to clarify for this slide or anything I talked about earlier?
Not this particular slide, but I just want to clarify something on the problem setting,
Okay.
which is the arc challenge itself. So do you think I think I'm not still not super familiar with the with this problem, but do you think it's something can be solved by in terms of if we talk about logic, do you think something can be solved by entirely using logical deduction, or you need to do some form of inference?
You're talking about which one? The arc challenge, is it?
Yes.
This kind of stuff, is it? Do you think it can be
Yeah,
solved using what?
logical deduction.
Okay, so using an LLM to deduce the logic, right?
Um, no, I'm just wondering, can this problem be solved with purely just deduction? Like given is by which I mean like strictly just like prove some theorem, like you just follow step by step very rigorously, as opposed to maybe you need some method like trying to infer some general rule, then based on the rule trying to come up with answer.
Okay, just for the ARC challenge alone, the rules are actually pretty much in a kind of very deterministic manner. So if you were to use the math way of doing the theorem, lemma, that kind, I think you can solve the ARC challenge. But then again, is that the best way to solve it? May not be, because you need to pass through the entire theorem tree or entire rule tree in order to find out what rules there are. Like for humans, when we solve the ARC challenge, we don't really like have this textbook of rules to look at. Oh, is it the same
Yes.
color? Oh, it's yeah. So it's a bit different the
Yeah,
way we solve it compared to if we use a theorem-based method to solve. Yeah, and for humans,
I see.
the way that I think we solve it is through differences. Like we just look at this thing here, and then we compare to here, like, what's changed? Oh, the number of like squares have changed. Okay, now it's only six. Okay, compared to over here. Oh, over here there's also six by six objects. So then we like do some matching based on like, oh, in object space, it looks like the thing has changed from six objects become six
I see.
pixels. Then we ask ourselves, how? How has it changed? You know, then there's some way of filtering the responses, and that is not native to like theorem approaches, because theorem approaches, what you
Yes,
do is you take a state here, and then you try out all possible rules, right? Like if you take a look at the hypertree proof search by Meta, they are essentially doing a like sort of multi-color tree search over like theorem space. Like they perform an action, then they get a certain state here, and sometimes the action will cause like two separate states that you need to prove. Okay, so only when these two states become a null state, okay, which means that the theorem has been proven. So only when this has become a null state for all the subtrees, then you have proved the main theorem. So here will be your main theorem. Yeah. So you can do this kind of way to solve the ARC challenge. You give it enough actions and stuff, you can probably solve it. That's also what quite a few people did in like the domain specific language. They try to use various rules of the VSL. Basically, VSL is like some functions. They apply the functions. Usually the functions are unary, which means that they take only one parameter like that. They do this function, and then they just keep applying the functions like up to that X, up to that Y maybe. Yeah. So you can do something like that and see whether in the end it matches the input to the output like that. Yeah, you could do that. I just think that it's intractable because there's just so many transformations you can do.
Yeah, so I think the interesting thing is how does if uh if LM can successfully solve it, what kind of method it employs to solve the problem if
Mm.
there is multiple ways of doing it. The reason I ask this question because recently I saw a paper titled Large Language Model, sorry, GPT-4 cannot do reasoning. Like that's literally its title. Then in the paper itself, they give a lot of examples, then basically some problem, then ask the GPT-4 to solve and it couldn't solve. But I realized I think all of the problems are of the form of logical deduction. So my own take is that maybe GPT-4 or large language model as a whole is not good at solving this kind of problem. That's why I'm trying to clarify, is this of the same kind of problem? Yeah.
Yeah, so natively, you know how the tokens are generated. You ask a question like that. So this is your question, and then you get your answer, right? So natively, there's no steps like behind the question to the generation step here. For large language model, is basically just using attention, self-attention. You know, we don't go through any tree search at all. Like we don't go through like, oh, you use this induction step. So if you are doing like maybe one inductive step, I think it's still okay, because um just one inductive step you might have seen in the training data, or if you put as context Okay, these are the functions these are the functions you can use. Okay, I find that in my own app challenge that I did, okay, the one that I like grounded on the function space, it can actually produce the output based on the function space I ground in, like multiple function space, like you add 2 or 3 combined together, it may still be able to do it. Okay, but that is a bit iffy because sometimes it can, sometimes it cannot. But if you are just doing only one function, very high likelihood you can do it if you ground it well in the context. Okay, and that's because like if you were to do next token prediction natively without giving any context, unless this transformation has been seen before in your training data, like for example, summarization of a text, we do this all the time for the benchmarks. Okay, so you don't have to ground it on like how to summarize. It knows, or sentiment analysis, it knows how to do it. Okay, but if you are doing something like, oh, rotation of a grid, you better ground it somewhere because it's not very native to a large language model to do this kind of operations. Induction, okay, like mathematical induction, is also not very obvious for okay, the problem with induction is that it's math, all right, and math itself is very rigid. Okay, let me write here, math is rigid, math is very specific and precise. Okay, large language models are almost the opposite of that. Okay, large language models are flexible. Okay, large language models are not very precise. Okay, so that is one of the reasons why it kind of doesn't do this kind of generation that well for logical reasoning, maybe because you must get all of the reasoning steps correct in order for it to work. And usually these are very, very specific kind of inductive steps. Unless you ground it on the kind of scope of steps it can do, if not, you just ask it to generate the induction step without giving any context. I don't know about the paper you mentioned, but if you don't give it any context, there's a very high chance you won't get the answer. Yeah, so yeah, maybe that's how they got GPT-4 to
Yeah.
fail.
I also have not looked into the details. But I think when we talk about reasoning, right, no matter what form of reasoning, we are actually looking, that's like kind of like emergent properties, right? So I wonder the fact that under the hood is doing next token prediction, does it really have a lot of things to do with that? Because like they are of the same different scale already.
Mhm.
I've seen another paper claim that LLM can do vision inference, but I think if we really literally take look into how it was trained, which is training an MLE fashion, right? Then how can it do vision inference? It doesn't make any sense. So personally, I feel that maybe we shouldn't focus too much on how it is trained, as in the next token prediction, because the reasoning or if it's capable of doing inference, right, then that should be viewed as in my opinion, should be viewed as a more of an immersion capability.
Mm.
So shouldn't just exclude the possibility because it's just doing next token prediction. Yeah, maybe more experiment need to run more experiment and need to check the details. Yeah.
I think
Yeah.
can I have a quick just
Richard, you
quickly.
are saying something?
Yeah, so just quickly, look, I think your thing around the LLMs are flexible and not precise. I think it's really the key thing is language, right? Math is its own language, and that's not the language they've been trained on. So the challenge for mine is to represent problems in words, right? There needs to be words present, and then inference is more helpful because and the words need to be meaningful. Right? So if the words aren't meaningful, there's no chance for a language model to work with them. And so I think so when I look at the LLM view, there's a bunch of numbers, but there's no words. And so the challenge, I think, is to find that representation where the LLM can leverage its strengths, not its weaknesses.
Yeah, well said.
Yeah.
Actually, that's like the neuro-symbolic approaches. So this is actually very much in line with that. So you need to have a representation space whereby you can represent math, okay, in some form of space where the large language models can do like token matching. So in this case, if you can represent your theorem as one token, A maybe, and then like for example, if you want to find out whether the number is even or odd. We can represent it by certain token like A, and then you can try to maybe classify the problem by like whether or not is it matching this one. Then you can do some form of like, like tree of thought or something. You can then say, after we classify the main problem, we can do a sub problem, which is then for each sub problem we ground it well. We ground the sub problem well in possible strategies or action spaces. Yeah, I can imagine something like that to work for induction actually. If you can ground this well, like basically you have different modules to do different things. Yeah, you can do both together. So in some sense, this is neurosymbolic because the symbolic part is math. Okay, math is very, very symbolic. It's like very rigid, and this is the neuro part. Okay, because it's more flexible. It's based on next token prediction, which is not very grounded in very precise relations. Yeah, you don't need to have like A plus 1 equals to B. You don't have to maintain that all the time because internally when we predict like, okay, like, sorry, 1 plus 1 equals to 2. When the large language model predicts 1 plus 1 equals something, it's not calculating 1 plus 1 equals 2. It's just saying that, oh, in the training data, okay, this 1 plus 1 normally follows with 2. That kind of, it's just doing this kind of like familiarity matching of some sorts. So yeah, if you could somehow like embed this kind of familiarity, or if you cannot do the familiarity, you can embed the way to solve it in some semantic space which is understandable and associatable by the language model. Like the language model can associate, oh, this problem should use this kind of semantic space. Then you can probably solve this kind of math stuff with large language models. Yeah. So whatever Richard said about representation part, I think that's very, very important, especially if you want to use large language models to solve it. But the more important question is, why do you want to use it to solve it? I mean, if you need to do math stuff, just use a math tool. Okay, because large language models are good for language. Okay, they may not be good for this kind of problems like induction or like doing this kind of symbolic logic. Yeah, that's all I have. Sorry, Richard, you all have anything else you want to add for this?
No, that's it.
Okay, if not, yeah, that was a good conversation of like how even GPT-4 can fail in this kind of inductive tests, and that really depends on how the test is structured, because this inductive logic is not native to large language model prediction objective. Okay, this is more of a precise kind of relation. So if you don't ground it well, like for this ARC corpus, they just merely take the input as an ASCII text like this, and then ask you to predict another ASCII text. We don't even ground it in like how it can transform. It didn't do too well. It solved only like 10% of the corpus, which is not bad because like it solves more than like a lot of state-of-the-art methods. But in the large language model method that I did for this ARC, I actually gave it the context of like certain transformations it can do. Then I prompted to think of how the differences are in object, pixel, in grid view. Yeah. So when I do it like that, right, I actually solve about 50 out of 101 training problems. I mean, the only issue here is the context length. I mean, it ran out of context length pretty fast if I prompted in too much context. So you can see this like 40% solve rate compared to like 10% solve rate if we just do the ASCII to ASCII. So how you prompt the context is actually quite important if you want it to discover the rules. And the best is if the rules are already made known to the large language model in some semantic way. Yeah, I'm just going to type here. Best if rules are made known to LLM in semantic way. Okay, so like I also type here like ASCII to ASCII without context is about only like 10% solve rate. Yeah, so yeah. Okay, so I think I would like to move on from here because actually I want to talk more about like the reward and the goal seeking behavior. So if you're okay, I'll move on from here. Okay, so I'll go back to like what I was talking about with the reinforcement learning stuff earlier. Like I find that learning just from the reward alone is not a good idea. Okay, because it takes very long to learn. Okay, you kind of need other auxiliary rewards like distance to goal. All right. Distribution matching, which is like how to match your predicted winning moves with a Monte Carlo tree search base winning move that you can improve based on that. So this one is actually something like tool use to get better outcomes. In this case, the tool is the Monte Carlo tree search, and then learn from the tool. Okay, so this is something quite interesting because I think if you want to get improving large language models that can do like multi-step reasoning, I think this is probably what you need to do. You need to keep refining the output based on the two outputs. And of course, learning from experts. So in this case, some stuff that you think is expert data, like recently the models talking about, Phi 1, right? You talk about code, but you learn from the textbook, you can actually do better with a smaller model. So like things like this show that, maybe learning just from rewards is not exactly the best. You need some form of goal. Okay, actually all of these methods that I talked about earlier, I just realized it's all about goals. The first one, the grid maze here, is goal in terms of like distance to goal. All right. So if you can find a way to represent distances, you can learn from that. The second one is about goal by iterative improvement. So like you have an original output and then you improve it from some tool use. Or like if you are talking about like constitutional AI, you can improve by prompting it with constitution. Yeah, so something like that. If you can do this, you may not even need RL. You can just use this to train your model by giving it a better output. So this is like alpha 0. And the last one over here, this is like the goal is some ground truth, like a textbook. So you can see all these methods have some parallels to modern large language model training methods. And none of this use rewards. All right. So why are we so hung up with rewards and reinforcement learning? Because it may not be the best signal. So let me just show you some experiments of what I did. So instead of doing like 2D grid wall, in order for simplicity, I'm just doing a 1D grid wall. We have boxes 0, 1, 2, 3, 4, and 5. We have two actions. A is moving one step to the right, and B is moving one step to the left. All right, and what we want to do is we want to reach cell 5 for reward 1. Okay, so I'm going to use the method that they did, okay, in the for the card poll, which is decision transformers. You have the rewards to go here, okay, at the front. And then what we'll do is we will have state action, state action, state action. So it's like state action, state action, state action, state action. So it's a bit different from like the original decision transformer, because if you look here, the original decision transformer has state actions, rewards to go, state actions, rewards to go. But if you look at the card poll here, it's also state action, state action, state action. So we do the method that they did in the paper, all right? And you can see that a reward of 1 means that the end outcome reaches cell 5. And a reward of 0 means it doesn't. Okay, so we can then give it the pattern that we want to output, like 1, 3, okay? So you want it to output 3, something, something. You can see that ChatGPT is not exactly that great. I mean, it kind of doesn't really like, this is what you want, but it gave you like 1, A, 2, 3. So it doesn't start with the reward of 1 here. Okay, so it's not very natural for, let me just put this here, not natural for LLM to know the first number is a reward. Okay, it's not natural at all. And in fact, the way the large language model interprets numbers is not natural as well. So there's two issues over here. You can see even GPT-4. Okay, now everyone likes to say GPT-4 cannot do this, cannot do that. This one really cannot do. Okay, this one, GPT-4, you give it a reward of 1. You see, it reaches 5, which is not bad, but you see, it kind of like, why did it do this? Okay, maybe because I didn't ground enough examples, but GPT-4 has this tendency to like extrapolate the pattern a bit more. Yeah, so if we just do like reward seeking, it doesn't seem to do that well. All right, it doesn't seem to know that what we want is grid cell 5. Okay, because this reward of 1 or 0 has not much meaning to the large language model. It's like, why do you want me to go to 1? Why do you want me to go to 0? Like, if you are the model, you'll be asking like, what is 1 and 0? What does it mean, right? I mean, if you are the AI model, I give you these patterns that like you'll be guessing like, why do I get reward 1 here? Why do I get reward 0 here? So this is This is exactly the case of sparse reward. Okay, sparse rewards, the model will be wondering, why is there a reward 0? Why is there a reward 1? It's not very natural for a large language model to know. Like, so there's 2 steps that the large language model needs to do. They need to firstly figure out what the reward corresponds to. Okay, which is like maybe the goal. And then secondly, it needs to figure out how to go. So if it fails to figure out like any of these 2 steps, it may not know what to do. So it's like giving it an additional computation stuff, which is this one here, step 1. Like, why do we want to give it the reward when we can just tell it the goal verbally? All right. Last time I can understand, because last time large language models didn't really exist. So the reward signal is the easiest signal to train on. But right now we can just give the entire problem in text. Why do we still need the reward? So this is something that I like to ask the RL community, okay? Because I think we have to change the approach that we do things, okay? This is an old approach. So next is goal seeking, right? So the exact same problem here, right? What I do for this problem is that instead of giving the reward, I condition on the goal state I want to achieve. So you can see that I can do the same kind of experiments, but instead of reward of 1, 0, 0, 1, I just simply change it to the eventual output that I want, which is like cell 5 or cell 0, cell 3. So immediately you can see one thing here. All right. You can learn from any experience. Can y'all see that? Can y'all see why I can learn from any experience if I do goal seeking? Like, you want to maybe contribute some reasons why you can learn from any experience? Richard, you were saying something?
Well, I think that you can learn from experience if you can, if you can define a goal and reach it, then you can make your own reward. And I think that's going to be the challenge. If you is the problem we find a lot in, say, industry, right? Where you talk about use cases and requirements and so on. And usually they're half the battle. I'd say we can build almost anything in industry today. You imagine it, you can build it. The real trick is getting people to figure out what they want. And it doesn't go away because you use LLMs, right? We still have that as a challenge. And it's a fundamental challenge we have. So, but if you can define the goal and you can understand that you've reached it, then you can use that as a reward signal of some kind, right? Or function or whatever, however you're going to manage rewards and reinforcement. But they become that benchmark, I think. And that's the trick, is setting a benchmark.
That's true. So actually, that's half of what I wanted to say. So Richard, you said correctly half. The other half is that you realize that this reward itself is defined by your last state that you entered, right? So technically, even if I don't reach the goal state, like I reach the state 0, what did I learn? Okay, if I fail to reach the goal, I can just create my own goal. You just create whatever state the agent lands in, that's the goal. So if the agent fails to reach maybe cell 5, does that mean that the agent learns nothing? No, it means that I have learned maybe a sequence of trajectories that can reach cell 0. So it's very flexible here. It means that I don't necessarily need to define a reward only when reaching cell 5. I learn how to reach any state. You can learn how to reach any state because any state that you have transited to is a goal, right? You can just define that as a goal. So in some sense, this is like next token prediction, right? There's no real reward here. We are just trying to learn how to predict the next token. Okay, maybe that's the reward. But learning how to predict the next token, you also learn how to perform transitions between like states. I mean, that's one of the inherent properties of learning next token prediction, is that you learn the structure of your data. Here, because we give the end outcome here as your goal that you want to reach, you also learn the structure of the environment, because anywhere you transit, that will be your goal. And then, maybe next time there's a use case of going there. So if I only did reward, I must relearn the reward. I must relearn the actions if I change the goal. Okay, can you see that? Like if the goal is to reach cell 5, I give a reward of 1 to reach cell 5 and reward of 0 not to reach cell 5. If I want to change my end goal to be cell 0 now, I kind of need to relearn the entire reinforcement learning process so that I can reach cell 0 by giving cell 0 a reward of 1. Right? Why do you think reinforcement learning only works well for some environments? Like RL only works well if environment doesn't change much. Okay, like for example, Go, chess, okay, and the end outcome is always the same. All right, it's either win or lose. You don't change this. The moment you change any of this, your RL algorithm is going to have a hard time learning again. That's because we use rewards that are conditioned to one specific kind of goal. You want fast and adaptable agents, you need to have some form of goal-seeking kind of objective so that no matter how you change your goal, the agent is still able to adapt and learn that. So I feel that this goal-seeking kind of conditioning on the goals is probably the right way to do it. Okay, yeah, that's all I have to say for this. You can see from the results that even ChatGPT got the right answer. I mean, granted, they didn't do the 5 ... but it got the right answer here. Same thing for GPT-4, which is an improvement because all these sequences are exactly the same as the previous slide. It's exactly the same as the previous slide. I just replace, instead of the number 1 or 0 from your reward, I just replace with the end goal. Okay, any questions for this? Or any thoughts that you have?
So keen to see where we go with what to do with this reward signal, right? So take your point. If you manage to achieve an outcome which is different to where you started, that's a goal. Well done. It's a learning opportunity, right? That's great. But I'm not sure is how we apply that, right, outside of this explicit training context.
I mean, you can learn from any trajectory of data. You can learn the signal, which is the goal. So in some sense, this is unsupervised learning. Like you don't even need a goal. You don't even need any rewards at all. You can just run the agent in any environment, collect simulations of it, and it can learn just from this goal-seeking objective. So I would say it's very, very flexible.
Certainly is.
Yeah, so I think this will be the new way of doing RL. Okay, we can forget about rewards, right? And I've been trying to advocate for this. Unfortunately, my paper has been rejected, so I'm trying to submit again. But I think this is the right way to do it. Okay, so this is the... Okay, so that was goal directed, right? Now I'm going to one step more than that, all right? What if I can do goal directed plus LLM-based descriptions? Okay, because earlier, you know, when I talked about like, oh, in the card pole environment, the human has been told, okay, you have a pole, you need to balance with the card, right? AI models right now, they don't really have this. I mean, there are some people who try to infuse like bird-based descriptions into a RL policy. It's still not that great because it's still RL. What if we can just give, okay, you see like what I did earlier, like this is the reward one. I just said that, okay, this is the description of the environment, okay? I give it as the LLM text. There's a grid wall of cells 0 to 5. Action A moves the cell to the right. Action B moves the cell to the left. Reward 1 when agent reaches cell 5. The sequences are given as reward, state, action, until 5 actions are taken or cell 5 is reached. Then these are the examples. So I just give it 2 examples like that. Okay, because this thing here is like something like 0-shot description. All right, because I give it a 0-shot description, my few short examples here can be reduced. Okay, so this is a trend that you see. So like there's these papers that said 1 prompt is worth 1,000 examples. So similarly, like if you do some 0-shot semantic meaning here at the front, you don't need that many examples at the back to tell you what to do. All right, so we can ask it to output several patterns like this over here. You can see that you got it right. This one is correct also because like 0 means I don't want to end with 5. 1 end with 5, correct. This one end with 5, correct. Last one here is wrong. Okay, last one it ended with 5 here. Okay, so if we just use like ChatGPT and we just use the description of the environment to condition as context, it works wonders. Okay, it solves the environment almost like without any examples. Okay, I mean, of course, you still need to give it this one here because you need to tell it how to output the sequence format. Okay, and unless you describe it so well that it knows how to do it from the text alone. If not, this is just to tell it what to do, right? So you can see over here, if we tell it the objective of when it gets the reward, it gets it like 4 out of 5 of the time. Okay, that's amazing. That's actually amazing because this is actually not a difficult. This is actually quite a difficult problem to solve because it's a sparse reward context, right? What if we did goal seeking? Okay, so instead of reward, now I do goal state. So you see, goal state is like that, 5 and 1, right? So I gave it like 6 of them here. Okay, you can see that it reaches goal state of 5, reaches goal state of 0, reaches goal state of 4, reaches goal state of 3, reaches goal state of 2, reaches goal state of 1. Are my actions correct? A goes to the right, correct. B goes to the left, correct. A goes to the right, correct. B goes to the left, also correct. B goes to the left, and B goes to the left. So let me just highlight this here. All correct. Plus description. So this is actually damn cool. I mean, like, you can imagine this applied to the couple environment. I think you can solve the couple environment almost zero shot. Like, without even needing any like simulations, you can just give the description of how you want to balance the pole. Like, if the pole moves left, no, actually that's a bit cheating. You can just say like you need to balance the pole, then maybe give it some examples of when the pole drops. You can perhaps do much better than what the paper did for couple. Like with just 1 or 2 simulations, you can perhaps learn everything already. If you can give the description, plus give it the goal. In this case, the goal is to balance the pole, right? If you give the pole as some arbitrary reward like that, like over here, you give some arbitrary reward like 60, 75, 98, what is the AI going to learn? The AI is just going to learn, oh my gosh, what a big number. What does this mean? But if I give the goal here, if I give it as a goal is balance the pole. That's a way more easier goal to achieve because I know, and what does the balance the pole mean? It means like angle below, absolute angle. You can even write this out in words, below 5 or like absolute velocity smaller than 5 or by 1. Maybe you can just write like that. I mean, it's not great at math, but if you can tokenize this somehow, yeah, that will be your goal. And your goal can be expressed in words. And like you can condition here the objective here instead of total reward. Your objective here will be something like this. Your objective will be 0, 0, maybe. Yeah, because like you want to achieve a state whereby the whole angle and the velocity is like that. So I'm just assuming that that's a 0 in this case. So you can see that we can easily do the goal-directed part in decision transformers. Right? We just need to replace the rewards to go with the goal, goal state.
If I can, just briefly, one of the questions I got is, so let's say there's a wall of numbers, right? And as a rule, computers are good at numbers, but we're not using large language models in that traditional way. Right? So in a neural network, for instance, this would make perfect sense, right? It's numeric data in, numeric data out, perfect. One of the things I'm trying to experiment on at the moment is by using words to describe degree. So instead of total reward 60, 75, 98, you'd have moderate, great, best. Right? And that's what I mean by trying to lean into this idea of using language. And so instead of describing the lean of the state of the system in terms of how far does it lean, again, you'd have the same vocabulary to describe how far it's leaning over. A little left, a lot left, it's falling to the right, whatever the words might be, and see if it changes the behavior. This is sufficient, but this is also a really easy problem, right? But the trick is again, you have to get a response back that uses the right vocabulary of move it a little to the left is very hard to turn into, a servo motion. Right? It doesn't really understand that. So we have to translate back out. One of my ideas was to try and just set up a vocabulary to standardize that and have it work in those semantic approaches to degree. Does that make sense?
Yeah. So this is a very relevant point because like you're talking about control problems may not be expressible in semantics. Like you may not have a right word to describe it. So maybe the language grounding is not natural for this problem. Yeah. So I do agree with this, and that's why I feel like this goal-directed decision transformers I'm thinking about, it can be done in two different abstraction spaces. And I mean, what do I mean by that? In one space, there's no language at all. Okay, we are just using the neural networks, and the other you can use the language, which is the description of problem. So that's a more higher level planning kind of stuff where you're talking about like how to move a robot from point A to point B. You know, you can say move your leg left, move your leg right, move your leg left. So you don't you don't really have to say that like move your leg left, move your leg right. You can just say I want to go from point A to point B. So this is the higher level planning. So like maybe you can do path finding at higher level without the exact motors, the motor outputs. You can just give it like maybe like path find x to y, something like that. You can just do a function. And the other side, which is the more low level side, this is the motor part, which is like you control the exact motor needed. And this part can be done using neural networks with no language. Yeah, because in this case, if we do just neural networks, we can better tokenize the numbers. I mean, because you don't no tokenization needed. Like you can better represent the numbers. Yeah, because there's this thing of transformers that have no tokenization. So essentially you just put in the number and this will be straight away put to your embedding space. So using a multi-layer perceptrons, your number can map directly to an embedding space. And this kind of preserves the magnitude of your number. Yeah, so I do think you need both one low-level component, which is not expressible in language, and at a higher level component, you call upon the stuff that takes in this motor part. So I believe this is necessary for complete system. You cannot do without either one. Yeah, because if you go too much into the motor, you cannot. This is more micro. You cannot really do high. This is micro level, which is like hard to plan ahead, plan for larger tasks or for macro tasks. And then this part here is too macro level. It's hard to plan for micro tasks. So both parts have their own use cases and both are necessary for like eventually getting a robot to move from one point to another point. At least this is my view of things. Yeah, y'all can feel free to comment on this. Okay, if not, I'm going to move to the next slide. Okay, I'm going to clear everything. So yeah, this is a very exciting thing. I really think this goal directedness is the way to solving the flaws of reinforcement learning. And just a recap, like this was the paper that I was writing. I intend to augment this with large language models. So right now, this is entirely neural network based. Like I just use a multi-layer perceptron. So the idea is given a state and given a goal, all right, I train a neural network to just predict an action. Okay, there's another pathway here is I do planning. So how do I do planning? I do planning by some form of, by looking up the tree of possibilities to find a source destination path. Yeah, so over here I did by like random simulation, but you can essentially use a pathfinding algorithm here. So this is the part where you use memory to guide actions. And then over here, this part here will be like instinct to guide actions. And if you can find something in memory that can tell you, okay, you should go this certain action because this has led you to this outcome before, you can then do this overriding part. So I call this fast and slow, all right, because this is the way like I think our brains kind of work. We have a very fast default network, and then once you want to do deliberate planning, then maybe you use the memory part. Of course, this part here, okay, I say this is deliberate planning, but I'm not sure, okay, because like maybe memory retrieval is automatic. Yeah, so maybe both are automatic. It's just the extent of which you do your planning. So yeah, I believe a combination of both helps because memory is very important in learning. But at the same time, even without memory, your basic gut feel of what you should do. Like for example, you eat chicken rice and you have a tummy ache. Next time you go to the chicken rice store, you might be like, this doesn't give me a good feeling. Like I don't have a good instinct about this. Yeah, this actually might help you to avoid danger already. Like you don't eat the same chicken rice store, but maybe you forgot that memory, forget that particular memory, but that instinct itself would already guide you not to do it. Yeah, of course, if that memory is still quite recent, you can retrieve it. You can justify like, yes, I remember I ate that store before and I got a tummy ache, so I'm not going to eat again. Stuff like that. You can use that memory to guide your actions. But if you forget your memory, which is what happens quite naturally in humans, at least your instinct network here will be trained. Okay, it takes a longer time for this network to be trained because like backprop in neural networks is a bit slow. Yeah, so this is slow learning. Okay, but after you learn already, you can actually throw away your memory. Okay, the memory helps to guide you fast. Okay, like you eat the chicken rice store maybe one time, you remember it, and then you don't repeat it again the next time you do it. Okay, that's like if you go the next day. Okay, if you go 1 year later, then this other network will kick in to help you to avoid it. So I think this is like more or less the crux of intelligence. This is like the model I'm proposing after my 4 years of PhD. I came up with this model as an alternative to AlphaZero because I think AlphaZero is not the way to solve intelligence. And actually, I intend to incorporate LLMs into both paths. So it was very exciting. It's very similar to what I shared today. Basically, we can ground instead of just giving it like a goal and a state in terms of like numbers. We can ground this in terms of some context. Maybe we can give some context to how we interpret this. You can give context as in text description of environment. That can be the fast. Okay. And over here in the slow here, this one we can give it like knowledge tree, context dependent knowledge graphs. Again, you can also ground this slow with the context as well. But when you retrieve the memories, it must be context dependent. So like all the videos I've done so far, eventually this will end up in this final system that I have, which is also called fast and slow, but it's fast and slow with large language models. So there's quite a lot of exciting things that I can foresee this happening. Right now, I'm already working with like Richard to do like LLM agents to solve like escape room problems. So eventually what we learn in that kind of environments will also help to be implemented in this kind of model. So yeah, I'm very excited to do this. This one is like my life kind of dream to finish this model. So once this is done, we will have very fast and adaptable agents already. So yeah, this is just a preview of like what's to come for the next 10 years or so. Yeah, so this is my kind of 10-year project to refine this fast and slow model. Okay, questions on this? Yeah, sorry, I talked quite a bit because I'm quite excited about this. Yeah, but do you have any questions on this?
I want
Okay,
to clarify it.
yes.
In your goal-directed model, do you specify the goal
Yes.
with explicitly with natural language?
No, in
So I
this
didn't
in
have
this
you.
in this paper that I did, the goal and the state are grid world. So it's like I give the X and Y coordinate of the grid.
No, I know this one. You talk. I mean, when you incorporate LLM, how do you then specify your goal?
So
Do
you can
you
specify
leverage on the?
based on, as what I said, based on the kind of micro or macro level planning. If it's micro level planning, the goal will still be a number, like some motor state or like some cell you want to go to. Yeah. If it's a higher level, the goal will be in text. Like I want you to fill up water into a cup. Yeah. So I can
Yeah.
envisage this fast and slow to have like multiple layers. Okay, this is a bit more complicated, but thanks for asking. So this one can be like the layer X. So you can have multiple layers of fast and slow. So you have top layer is the macro use language, and then maybe the bottom layer is micro use numbers or motor representation, grid cell. So like I can envision like whatever I did for this paper will be more of the micro level, at a more macro level, then you talk about like context in text. Yeah. So yeah, that's a good point. So like this plus LLMs, but will likely be for a more macro level kind of planner. Yeah. Which means the actions will be more macro, so like path find, like the action will be like a function rather than the actual action itself. That's whatever I say makes sense.
Need to think more about it.
Yeah, maybe I can show the iJapa video, the picture, like you have a top layer here, your top layer makes a certain action. This action will then be like the goal. Okay, so you have a goal at the top. Your top layer will make a certain action, and then this action here will be the goal for your bottom layer. So this one is actually like a goal. This because the action at the top layer will be a goal, and at the bottom layer, this action here, okay, will be your motor actions. So I believe that the intelligence is a hierarchy. At the top level, you have a main goal. You go through multiple levels. Each level gives you an action, which is the goal for the lower layer. And then, like for example, if you were talking about moving, like this one, the top layer, the goal could be like go from point A to point B. Okay. And then the first action that you do here, okay, maybe you have a sequence of actions like left leg forward, right leg forward. So like the first action here that is executed, left leg forward, maybe you can say moto A forward by 5 degrees. Yeah, so from the macro level action, your left leg forward here would be like the goal for your bottom layer here, which will then interpret this and then convert the moto A to move forward by 5 degrees.
If I can, say in the Minecraft papers that you were looking at, where that has a mid-level API. So for them, the top level goal would be something like make a pick, craft something, right? Whatever it is. But then it breaks that down into, and its bottom level is walk towards the tree, or walk or run away from the zombie, or whatever it's going to be. And actually, the API itself takes care of everything below that. That's not your problem. That's just how the game works, or how the API works.
That's because they abstracted the bottom layer stuff into the API.
Exactly. Yep. Yeah.
If you wanted to learn the bottom level stuff, you will need a bottom level kind of neural network to learn something.
Yeah, exactly. Yeah, absolutely. But yeah, in terms of the segregation, though, it's a nice. They packaged it up exactly along those lines. As a user, your job is to figure out what you want, then they'll figure out what's needed in the game to do relatively fundamental tasks.
That's why I like the Voyager paper quite a lot, because it talks about more high-level planning. And I can envision this to be in the eventual kind of learning system where you have a high-level planner, you have a mid-level planner, lower-level planner. All of them are trained using unsupervised learning, which is like incidental learning. Like, because I learn based on goals, and I will always achieve the goal, because like, let's say if I don't reach point B, what will happen? It means that I'll reach point C, right? And I can learn from that. I can learn how to go from point A to point C. I will always learn something. I don't have to learn based on the reward of, yes, reward 1 for reaching point B. I don't have to do that. All levels of this hierarchy, of this fast and slow, can learn using any goal. And this goal is incidental. It will learn from whatever goal that your agent has encountered. And all of them will have both this fast instinct-based and the memory-based. So both are hand in hand. Because memory is used for fast learning, which is like you have one memory instance, you can learn from that. And this instinct here is used like for a longer term. Like if you eventually forget your memory, which you would happen, you would forget some stuff because it's hard to retrieve, because there's just too much stimuli to remember. You will store this like ground knowledge in your neural network. Like sometimes I do certain actions, I don't even know why. It's just so used to me. Like, you know, when you take a towel and dry yourself, you have this certain action that you do. Why? Why do you do that action? Do you realize you repeat almost the same pattern of actions every time you dry yourself with a towel? That's because it's in the fast kind of neural network. You already have learned it, and there's a reason why. Like maybe you want to dry a particular area, and that's how you've been doing it. That works in the past. Yeah, I would like to highlight one thing here. Okay, the output is not guaranteed to be efficient or optimal. Okay, I would like to say that, like, because of this goal-directed learning, okay, we don't necessarily search all possible trees of actions. We are just maybe searching out of all the stuff we encountered, what is the best or what's the most efficient. So unless you search every single pathway that is possible in the world, okay, it's not guaranteed that you will get an optimal action.
I mean, I think, what you're saying, I think is completely right. We see that in the Voyager paper and similar, right? So it comes up with really bad solutions, but they do work. And people do that for themselves. It becomes habit and they continue. But at some point, we have enough experience to estimate there's got to be a better way, right? I've got to go back
not all the time though. Like,
no. Yeah, like some people love a terrible solution, right? But so there's a personal distinction there that people make, right? But some people are never happy and they're always going back and trying to make a better mousetrap or whatever. They're probably in this meeting. And then there's the other people who are just happy with whatever they're used to and they don't like change, right? But how do the challenge is, it's one thing to have a solution that will work even if it's inefficient, and that's much better than having nothing. But then how do you go back and say, but I can do better, right? As we talk about, like, the hippocampal thing as you're sleeping and your body sort of cleans out unnecessary bits of your brain, reclaims them for something more useful, right? That it's a continuing pattern of reevaluation of knowledge and structure. And I couldn't, when I was thinking about this, I couldn't see the pattern that says we need to go revisit this and see if we can do it better. I couldn't figure that out. And if you've come across that or looked into it, I'm sort of curious.
You mean why we dream certain things, right?
No, not necessarily though. I think that might just be a side effect. But it's the idea, this pattern of where, say, physically speaking, when you rest, extraneous neurons, say unreachable ones or the ones that haven't been exercised for a long time, can actually be consumed by the body as energy or something, right? They're just gone. On the other hand, when it comes to personal habits, there's one way to make, go to have lunch, right? And maybe you've had the same lunch every day, all day, because that's what you do, right? Now put into a new environment, maybe that actually becomes a lot of hard work instead of being automatic. So you go from being working at home to working in an office. You don't have a fridge full of ingredients. You've just got whatever you take with you that day. Right? So now you need a new solution, right? And that's the thing I'm trying to get to. That realization, that critical examination of self, of your own history or of your own activities, that says this doesn't feel right. Right? There's something here needs to go.
In some sense, it's something like your fast neural networks trying to, like, tell you that, hey, you should be doing something else. Maybe that's because, like, you realize that the state that you are in right now has changed. And then, like, because your memory over here, like, tends to override your action, right? Then your fast neural network, maybe, like, if there's a dissonance for too long, your fast neural network might say, hey, maybe it's time to change what we do from based on memory. Maybe it's time to do something else. Yeah, so I guess there might be a feedback system from your instinctual kind of habits to tell, like, your habitual stuff, like, okay, maybe it's time to do something else. I don't know. So this is something that I didn't really think about before, but yeah, when the context changes, your consciousness somehow knows that you need to reassess, right?
Yeah, or even sometimes I'm bored of this, I need a change. Right? And so that's the sort of curiosity response, but there's also
a higher level system affecting this.
Yeah, but I think I feel like there's a pattern there that needs to be reflected. That's all.
That's an interesting suggestion. Yeah, let me think about it. I mean, regarding, like, during the sleep, your neurons got eaten up. I think that is a reflection of pruning also. Like, I did some work on pruning year one. So I think pruning helps to make the pathways more efficient. by removing away those stuff that is not needed at all, your output pathway will be more efficient.
Yeah.
Like,
And
so
I think that's true, but again, that happens to the higher level as well, right? That's the thing I'm getting at, is this pattern I feel repeats in many different ways.
Perhaps. Because actually eating up neurons or removing neurons from the pathway is a form of learning. You learn that these neurons are not needed. Yeah, I mean, you think about it, yeah, pruning does help the network improve performance in some cases. Yeah. So yeah, thanks for sharing. I think those are interesting insights. If ever this system is created, then this is like my life dream created. Yeah, so I think we still have work on this. This is not the answer, definitely. This is just like my view of it after looking at this problem for a long time. And there's also one other part here that I didn't talk about, which is called multi-agent, because like each agent can have different characteristics. And then actually you can learn from each other's experience. So there's this thing about memory. This memory over here need not just be your own memory, okay? This memory can be a learned memory. Like, we can learn memory from others also. Yeah. We can also use other people's memories to help guide us. And that's the case for children. You see, they mimic adults quite well. They can mimic other people's actions, and that will become part of their memory, because when they mimic other people, they have done it. In fact, I don't even think you need to do the action to infuse that as memory. Just thinking about it in your head may be sufficient to put that form of memory inside higher level circuits. So this multi-agent thing is perhaps the key to intelligence, because a single agent can be very focused on a certain maxima. Like, for example, now everyone's talking about large language models, right? Everyone's just focusing on that. Maybe we need other methods in addition to this. Then, when someone else has created another method, it's like, oh yeah, maybe goal-directed learning, something like that is needed. Then, you can learn from other people as well. So if you just only have one agent narrowly focusing on performing stuff that they're already very familiar with, yeah, that may not be enough. You need people to have various experiences, share ideas. That's how we learn as a species, all right, as a human population. So I think this idea of multi-agent learning and sharing, that's something that perhaps is the way to do some form of improvement as well. Yeah, so this is a different topic altogether. This is like, I'm just giving this whole picture here because since I already talked about all this stuff that is in my head for a while, this is the last part of the puzzle that I have. Okay, yeah, maybe just like 1 minute here. Any other things you want to talk about before I go on to conclude today? Okay, yeah, thanks for the discussion. It was helpful. So yeah, this is the fast goal-directed network. As I said earlier, like, you can actually learn from past states. Like, any goal state that you reach can be a state that you learn. So your start state to goal state, you can learn any trajectory. And if you do planning here, you can also learn from your planned goal state here as an experience. So very, very, very flexible and dynamic. I like this idea a lot. So yeah, this is part of the original paper of fast and slow. Okay, so this is the goal-directed decision transformer I was alluding to. So I like transformers, okay, but I think the idea of using reward is not correct. So if we could do something like a goal state conditioning, okay, instead of a reward here, you condition on the goal you want to achieve, okay, you can perhaps perform way better than using rewards. I mean, I showed some experiments using the large language model. It learns way better using the goal as compared to reward, like a perfect solve rate compared to maybe like 4 out of 5. I can't remember what's the reward-based solve rate, but yeah, or if I remember correctly, if I don't constrain on the description, you solve 0. Like, I only did 1 trial, but you can see that the goal state conditioning is way superior compared to the reward-based conditioning, right? And the benefit of this is that if your goal changes, no need to retrain the whole model, because you don't have a reward-based objective anymore. Your goal, if let's say cut pole, your goal is to make the pole drop down, you don't have to train a new reward for that, because you already, based on the goal directedness, you already know that, okay, how do I go to upright position? How do I go to a flat position? I can just recalibrate my actions accordingly. So I think this is very, very flexible. Yeah, if people are interested in this, like, so if you want to do this with me, you let me know. Yep. So This is something that I think will work. Yeah, it's just that I haven't done the experiments rigorously yet, but I know this will definitely work. Okay, so let's move on to the conclusion. So we have shown in this paper of the large language models as pattern machines. LLMs can do off-the-shelf generalization quite well to out-of-distribution problems. Provided that the tokenization is correct, you can use some semantic meaning to like sort of match the distribution. Yeah, LLMs are very good in context learners. Okay, but if you want to do like better association, like if you want to do like inductive steps, like math inductive steps, it's best to help to use it in some abstraction space. Like if you want to do math, you need to do some semantic meaning for the math for use case. Yeah. So in the up challenge, you can do like object view, pixel view. You can have various useful abstraction spaces for that problem. It can help to do the association from input to output better. Numbers, okay, it's best not to use it. Okay, in my experience, it's best to do by categories. So you ask it to classify into certain bins. Yeah, and the last point I have to make is that reward-based stuff is not that great. Okay, you should use go-directedness instead. It learns way faster, and you can learn from any experiences. So, yeah, I'm quite positive that this kind of things will work. And yeah, so these are some questions to ponder before we end today. The first thing is, sequence modeling, or is sequence modeling for all types of sequences natural for transformer? So maybe I just answer first, then we can invite some time for you all to answer as well. Like, I feel like not all sequences are natural. Like, if you talk about numbers, are not natural because the embedding space are usually meant for words, right? So if you cannot tokenize it properly, like sometimes your tokenization might also be, tokenization might break up the meaning. So sometimes for the use cases that are very different from the training distribution, you can have this issue. Like for biomedical cases, if let's say your word like calcification, okay, that is not a very common word. It might be interpreted differently. So this is some kind of stuff like where you talk about like model sequences. Sometimes this would happen. Like in the paper, they did the cut pole thing by just text, like 45, 50 for the state, then 1, then 44, 49,2, something like that. This is not very natural for the large language model because the large language model, okay, it might actually tokenize this differently from intention, from the intended way you want. So this is something to take note of. If you want to use large language models for arbitrary pattern machines, better make sure that the tokenization is tokenizing it correctly, and the semantic meaning is not overriding the token. Yeah. So in the last week, we talked about how like you do foo and bar at certain places, you can break the semantic meaning. Yeah. So that's something that you should take note of.
Has there been any investigation into, I mean, the reason numbers are tricky is they have their own relationships, right? Outside, they have their own semantics in maths. As you say, they're very precise. And they're highly, those relationships are extremely highly dimensional, right? So if you take the number 3 and try and relate it to all the other different ways, what you can do with the number 3, billions of possibilities just for one digit. So you can see 3 as a digit printed on screen, where it's 1/2 of 33. You can look at it as multiplied by 11, it becomes 33. You can look at it as the square root of 9 and so on and so forth, right? So I think, I suspect that kind of, to treat it as a sequence, numbers will always be compromised, I suspect.
I agree. Yeah, that's why large language models suck at math. There's a reason. Yeah, there's a reason for that.
But even I think they suck because the tokenizers aren't attempting to represent those relationships, those sequences, and I don't think I suspect there's something fundamental that says they can't.
Yes. You see the way to. Oh, sorry. Who's speaking? Sorry, is it?
I beg to differ. I
Okay,
think
yeah,
there's
please go ahead.
nothing fundamental prevent from having good representation for numbers. I think it still boils down to the what kind of data or text have been trained on. So I think it's already a common understanding that for the current, like at least I think for the current version of the model, for the past few months have tried, right? It is good. It is very good uh, on certain topics, whereas it's not so good. It tends to hallucinate more on certain topics, and it's known for not good at doing arithmetics. But however, it's good as coding, right? So I think it has a lot to do with the training data itself. Um, I know there's a work that improve the arithmetic capability of some smaller model to beat GPT-4 because the training data. So I think to a very large extent, for example, just now I think Richard mentioned that the relation of between numbers, they are very complex. But I think given just imagine a mathematician given so many years of experiences of working with numbers on so many different kind of question, right? You still will naturally form this intuition. You have this representation in your mind. I think the same can be said for language model. It's my hypothesis because I don't have any solid evidence at the moment, but yeah, that's my hypothesis. It's just I don't feel there's anything fundamental preventing LM from learning a good representation,
I,
given good data.
I mean, there's something to what you're saying, right? There is. I think the challenge at the moment would be, I'm trying to imagine what the tokenizer would look like, right? Because that's where this battle will be won and lost. I think the transformer models that are being used are completely capable of taking on almost any kind of pattern. But the challenge is to represent the numbers in such a way that the patterns that are relevant can be approached by a transformer. Otherwise, and I suspect what's happening in the small models you're describing today, that they're just memorizing, as it were, they're compressing their knowledge of the a bounded set of maths problems. Does that make sense? That's, I suspect, and I haven't looked into them. So
I
Yeah.
think that's
So
a valid hypothesis. Yeah.
so I think the way to represent numbers is do away with tokenization altogether. You just use an MLP, go straight into the embedding space. Okay, then in that case, you can preserve the magnitude of your embedding because, I mean, we talk about MLP, you don't do those kind of hard cutoff. If your number is like 1, your embedding space will be a certain embedding space. Your number is 2, your embedding space will be like, maybe your embedding space of 2 will be twice that of 1 in terms of the magnitude. So stuff like that, if you preserve the embedding space in a certain sense, like based on the number itself, you could do arbitrary stuff like, if in your training data, if 1 plus 1 is 2, 1 plus 2 equals to 3, okay? And provided you know like the embedding space of 100, you can say 1 plus 100 is 101, okay? If not, you're going to have to learn for all possibilities of addition of any two numbers, and that's impossible to learn because there's just infinitely many possibilities. You need to represent the magnitude of the number somehow in the embedding space. If not, you cannot do math. Or you cannot do math out of distribution. You always have to be in distribution. But then there's another question, you see, humans also suck at math. Like, why do we want the large language model to do math? I mean, yeah, it's asking a fish to climb a tree, right? I mean, it's not meant for math stuff. Math should use a calculator. You use very precise tools. So again, it depends on what you want to solve. If it's just for an interest thing to see whether LLMs can do math, sure. But I would say that it's much better to just use LLMs for what it's good at, which is like associating between semantic meanings, and use tools for math, like calculators.
I agree that, I mean, I'm just saying in principle, nothing prevent it from being good, but probably at a very great price, right? Very high price. So why not just use calculator?
Yeah. I mean, yeah, you're using a tool that you're using LLMs that are not meant to do math. to do something that is not meant to. It's like LLMs are also not meant to do inductive reasoning. Yeah, you should just use inductive solvers for that. Yeah, I can see a lot of people trying to use LLMs for everything, but that's not the way it should be. You should use it for what it's good at and offload those things that are not good to something else. Okay, I think we are more or less in agreement that not all sequences can be represented based on sequence modeling. All right. The next one is, can we zero-shot learn the rules for any sequence transformation, like the ARC challenge? Okay, so actually I have a very clear answer for that. The answer is no. Okay, it's just not possible. Like, so you mentioned about the induction, like GPT-4 cannot do induction, and that's if it's not provided the rules. Okay, so it cannot learn any arbitrary rule just like that. You have to ground it somehow, especially for stuff that is out of distribution. If rules are out of training distribution, very likely you need to provide rules in the context. Okay, if not, you have to do fine-tuning on your new distribution. Yeah. So I would say no, it's not possible to zero-shot the rules to learn it, okay, without being provided with any examples. Yeah. Okay, I guess you're in agreement for this, and any other views for the second part?
I think even for all of distribution, that's already a very bold claim. For the paper I've seen, right, they claim for few shot learning or in context learning, they are simply trying to locate the latent concept or relevant knowledge from within distribution. So it's still form of interpolation. Yeah, but all of distribution is like extrapolation. So
Yeah,
so it's even harder. I'm not sure if it's possible.
it can be possible if you ground it enough. So prompt engineering for our distribution is very important. Yeah, if you cannot prompt engineer due to the amount of words needed or amount of tokens needed, then possibly you have to look at fine-tuning. Yeah. Okay, the next question is, should we imbue semantic meaning as context to LLM? So it's like, rather than just asking it to get reward itself, we tell it like in words what you need to do. Like you need to balance the pole and stuff. Okay, the answer is probably yes. Okay, because it improves performance. And I've seen this in the ARC challenge. I've seen this in the goal-directed modeling that I've done using large language models. Giving context with semantic meaning is very, very helpful to solving both in distribution and out of distribution problems. Very, very helpful. Okay, it's like telling the model to think step by step, but giving it some examples for each step. It's like, oh, step one, you can use either method A or method B. You can describe those methods, or you will get very good analysis of your problems, at least based on what I've experimented with. Okay, lastly, should we learn by reward or goal conditioning? I think you all know my view. Yeah, my view is definitely goal conditioning. But I feel like we have been too focused on reward for too long. You know, like, I think this is an inferior method. Okay, so I dare to say that reinforcement learning with rewards is not the way to go. Yeah, we need to change that point of view. And yeah, that's.
I think the challenge is going to be where there's, I think like most of my life is in the industry, right? So in industry, it's very much outcome based as a rule, right? And it's a part of the way that organizations think. They think about risk reward. They think about, at every level, right? It's sort of from the macro to the micro, from individual goals and targets. If you're someone answering phones in a call center, to the chairman of the board, who's nominally answerable to shareholders for share price performance, right? It happens. It's just the way that organizations approach being an organization, right? And so it's a really, you were talking before micro and macro planning levels, right?
Yeah.
At a macro planning level, reward is going to have to be the way, which is really annoying because you get these sparse rewards.
Why though?
Right?
You could say the goal in terms of a language, like go from point A to point B. Like why do you need a reward for that?
because also there's even an implicit punishment for not making it, right? It works both ways. And it's actually a cultural problem rather than a technical problem I'm trying to describe, I think. In terms of, goal conditioning is a little bit like an agile development project where you go, well, we don't know what we're going to get finished this week, but we know we're going to do as much as possible. You try telling an accountant that, they have absolutely no patience for it, right? It's now accepted that is the way to get things done faster. But actually the accountant doesn't care what you get done. They care that they get their widget for the money they spent.
But in this case, your use case is also a goal condition use case. The goal is to produce the product.
It is, yeah. And so maybe I'm splitting hairs a bit, but that's what I'm trying to get at is it is a bit of the semantics matter, right? And what we were talking about earlier, where you say, you condition for a goal, right? Where you got to is a goal because you've achieved change. Good, we like that. Right? So, but is not the goal, right? It's not where so there's these two approaches maybe where you can have gradients for your reward, right? But if you look at a reward or even a goal conditioning approach, so you get you reinforce that if you want that outcome, this is a means to do it. Well, so we'll keep that for later. That's worth keeping, right? We'll condition on that. We'll fine tune or whatever we're going to do. Conversely, if you should actually get to the stated ultimate thing we asked you for, then then the gradient for your reward is much higher. There needs to be some way to acknowledge that, because that's actually the thing we asked for in the first place.
I understand. Yeah. So it's
Mhm.
outcome based in terms of you must produce the product. So that can be a reward, which is the product has been produced. As compared to goal conditioning, in this case, you're talking about step 1 has been done, step 2 has been done. That's not important. You need to get to the end goal.
Yep.
That's why. Okay, so I can actually address that concern. In goal conditioning, by conditioning on the goal itself, like for example, from this state here, we want to get to another state here. Let's call this S prime. We take maybe action A. And then if we go from another state, we take action B, we get X prime prime. Yeah, so it's in the hopes of goal conditioning that your state and your actions can be represented in the right abstraction space. Okay, so that given any arbitrary goal like S prime prime prime, you can perhaps just find a vector between these two here, and then your action here can be inferred from this vector. So it's like, how do I put it? Like, I think that if you do the goal conditioning right, it'll be easier to achieve like this desired end goal state as compared to just using a reward as an objective.
You get transfer learning, right?
Yes, yeah.
Right? And if you can do, like in teaching kids, transfer learning is the goal, but it doesn't really work very well. And you get these emergent effects. That's what we're looking for, right? And I agree, and I can see it. I just think it's I don't know. I feel when we're talking about semantic sort of systems, so LLMs, for instance, as we're saying, they work much better at these macro planning tasks. Right? They don't do well at detail. And the challenge is, are we applying the goal conditioning or the reward systems for a macro or a micro style solution? Do we need different mechanisms? I don't know. Maybe. Is it the same thing? I think I'm really interested in what goal conditioning does. I haven't applied it enough to internalize it.
Yeah, no worries. You share similar sentiments to my reviewers who all think reward is the best. Yeah, so it takes a while.
I think
it takes a while for the academia to get used to this idea as well. But I'm very sure my idea is correct. Yeah, I'm very sure this idea is correct. The goal-directed way is the more efficient way to learn. And it's also very natural because actually any reward that you have in mind can be expressed as a goal as well. So it's actually very versatile. Yeah.
The way I see this problem, the way I see the reward versus goal conditioning, right, is it's almost like the argument between explainable or deep learning. It's like I feel like they are just designed for different purpose. For example, I think just now we talk about micro versus micro, right? So in my understanding of formulation, basically the reward, like a scalar reward account, is for the account setting where you can have a well-defined um learning objective that can be represented by some number or some scalar. The problem is in real life, in a lot of situations, if you do that, there will be a specification occur, where by which I mean, um, in a lot of cases, like the reward is not good enough to represent what you actually want to achieve, your actual objective. So in that case, I think goal conditioning can be very useful. Whereas in a simpler setting where you can use you can define a problem with pure mathematics, without this misspecification, then you can just go for the reward. So I feel like they are just like for different use cases. Yeah.
I
But uh granted, like there's a lot of issues in real world. It cannot be well defined just by assigning reward. That's because there's this misalignment problem.
Yeah, I take your point. Actually, reward is useful in some cases, and goal conditioning useful in others. But I would say that the use cases for reward especially lesser than goal conditioning, because like reward, you see, you don't really have a fixed goal that you are headed to. It's very hard to verbalize that goal using just a reward. But if you cannot verbalize it well in an environment, like it's a very complicated environment, like you want the robot to fall with an angle of 5 degrees and not fall down with an angle of more than 80 degrees. Sometimes it takes very long to write that down. But if you give a reward, maybe it's faster to learn from it. So yeah, I would say that there are some usefulness for reward, especially when the user itself doesn't even know what gives a good reward. Like all the model-free reinforcement learning methods, you don't even need to tell the agent what to expect. The agent just randomly plays around and does something.
If I can, I'm reflecting on a conversation I had with a friend of mine, and we were talking about he's got some issues with work. He's got, and we talk about different ways he can approach the organization he's working in. And I was a bit old on him, and I was saying, well, if you do this, then that's going to upset a lot of people, and if you do that, then it may not be effective. And I know that because I've done both things at one time or another, and I upset a lot of people, and the other one wasn't very effective, right? So in terms of goal conditioning, it's interesting to keep in mind, I think, that your action A will get you to S prime. S prime may not be a thing you want to do again, right? So there's goal conditioning is real, right? I get it, that what you're saying, but there's also that may be an undesirable state that makes action A a thing to be avoided in future. And I think that is probably, you talk about context dependent behaviors and so on, and learning trees. And I think they start to relate into one another, where you can go, well, so reward is unambiguous. What's good about that, right? It's unambiguous. You've done a good thing. Here's your payoff. Good work. Goal conditioning, it's more ambiguous, which makes it perhaps more contextual and arguably in some cases better. But not all goals are good goals, if that makes sense.
I mean, there are some cases whereby you want to avoid certain states, right?
Exactly, right.
But you may not be able to avoid with the reward objective as well. When you explore, you might hit those states as well.
The reward answer is more training, right?
Yeah. I think that's not a big problem, because if anything, the goal conditioning, if your action spaces have the same sense of, like, for example, in the grid world, if you move upwards, you always move one square up. So you essentially learn the idea of moving up using goal conditioning as compared to reward, because reward, maybe you need to reach all the way to the door to learn something.
Yeah.
So in some sense, goal conditioning will help you avoid those undesirable states faster.
Yeah. Well,
yeah, so
I think that's the thing is
yeah.
to classify. You may need to classify which goal, in this context, is that a good goal?
Yeah, I mean, if the goal is not good, maybe you can have a list of stuff to avoid, and then you try
Exactly.
your best not to reach those goals. So you can also condition on not reaching those goals. Yeah,
Yes.
that's an interesting point. Yeah. But definitely, I think whatever drawbacks you talk about of goal conditioning, I think it can be easily solved. So I don't see any issues with this method. Yeah, but of course, don't worry. One day this will come to light that this is better. In fact, reinforcement learning has already goal-directed stuff as well. We have a goal-directed value function there. But I'm trying to do something even more radical. I'm saying we don't even need the value function. We can just learn from the goal itself. A sequence of actions and states conditioned on the goal you can really learn without the reward or without any value functions. So my claim is even bolder than what is claimed in most of RL literature. Yeah. Okay, if not, actually, thanks for the discussion. I kind of got to go already, but overall, this is a great discussion. I learned quite a lot as well. Overall, this paper of large language models as general pattern recognizers, an interesting paper. Although I think they did some of the stuff that is not in a great way, like for example, representing numbers, okay, may not be ideal for a large language model. Okay, representing this kind of rules, okay, without the context may not be great as well. Okay, and lastly, sequence improvement, if you just use reward instead of like conditioning on a goal, may not be the most ideal. So there are certain things that may not be great. Also, there's one other thing that they talk about. They talk about random tokens achieve similar performance, or achieve some performance. Okay, although it achieves some performance, but this is not ideal. So this method that they propose of random tokens for even like up challenge, I think this is not the way to go because tokens still have some semantic meaning from the training. So granted, there are some issues that I have with some of the paper. Overall, this paper has been an eye-opener in the sense that it has caused us to view the large language model more than just using for language itself. You can use it for arbitrary token matching stuff. And I think that is an interesting thing to take note of. Okay, if not, yeah, thanks for coming and I'll see you all again. Okay, bye.